Thank you very much for coming. Some of you were here late yesterday night, so I'm going to try to not repeat too much of what I said yesterday. It's very funny. We heard a lot whether deep learning is HPC, whether deep learning is hyperscale, whether it's supercompute. I don't have the pretension to answer those questions. For me, all are problems that we're familiar with and that we have to deal with when we do deep learning. So I'm going to say that deep learning encompasses all those worlds, and we just have to make do with it and be the best at it. So that's what I'm going to try to show today, and I'm going to try to show why. Quick intro. Not everybody might be familiar with deep learning. And I was asked yesterday night, so what else can we do than the image stuff we see all the time? And that's what we can do. The reason why deep learning is so hot is because you see it everywhere. Each time you upload a photo, like if you use Google Photo, for example, and if you've been skiing and you have a bunch of pictures with the snow, it offers you to just like winter or like to search in your pictures using words that you never use to tag those photos with. And that's where you can see deep learning in action. And you can see it in a bunch of like other areas. Automotive is a very famous one. We're going to come back to that. GPUs and deep learning. So that slide I'm pretty sure you've seen before. And I'm going to try to decipher it. We always say that GPUs are great at deep learning because they are parallel, they perform matrix operation, they got a lot of flops, and they can do bandwidth. And we say, oh yeah, that's the best thing. But we never say why. And after 2 years at NVIDIA, I started teaching again this year, and I had a student say, oh yeah, but you didn't say why. And I'm going to try today to show you why. So those are the applications you might have seen earlier. Same thing. It's a slide I'm pretty sure you've seen 20 times already. That's not the fun part of deep learning that I like. What I want to show is like deep learning is also something different. So for those of you that were here yesterday, this is a text that was fully generated using deep learning system. And as training input, somebody put the book King Lear from Shakespeare. So as I said yesterday, I never managed to finish it. So I don't even know whether that text is generated or not. But it looks very much like the real text, but it's not. And actually, Andrej Karpathy at Stanford did that. He did set up a system to train on text, any kind of text. And that's the kind of results he has. I give the blog entry here because it's a very interesting read. And I was saying yesterday, yeah, that's fine, but that's literature, right? In this crowd, usually nobody cares very much about it. The funny thing is, he trained that system with the Linux kernel, and he could actually generate code that would compile. The code wouldn't do anything interesting, but it would compile. And that's where you see the systems have gotten very, very good at being generative. You can also generate like funny stuff. Like you can train on a bunch of images saying, hey, those are Victorian paintings. And then you train a generator, and you tell the generator, hey, can you make me new Victorian paintings? And actually, the generator can make Victorian paintings, which is very good for me because I can't draw. I can code, but I cannot draw. And yeah, I was able to draw that time. I was very happy. The good thing is also, we talked a little bit about that yesterday, but that's fun, is you can perform operation on the images. And what I like very much with that example is something we can't really do, even in computer vision. Say, hey, give me a sunset. It's a cloudy one. Could you give me clouds? And then give me a beach. And what I'm going to ask you to do is I'm going to ask you to take that sunset, remove the clouds, and add the beach. And then I end up with a sunset at the beach. And this was fully generated from the system. I just gave him arithmetic on the images, but I didn't generate the sunset at the beach itself. So another cool example, I just give you that so that in the slide you can go and see the video. This is the latest CES video. This is the NVIDIA self-driving car, so I'm not going to show more than that, but it's very fun. Especially what's both great and freaky to me is that this is on an off-road, and you don't need to put your hands on the wheel at a speed which is kind of already too fast, what I would dare to do. So that's how far we are right now. Okay, neural net. I'm going to be very simple here. For me, a neural net is just an evaluation of a complex function. And for facial recognition, I just map a bunch of pixels to a name. For handwriting recognition, just an image to a character. For speech recognition, it's just a timeline sequence to some kind of language. And so for me, it's just going to be a network of simple interconnected neurons. And those are just made of two stages and perform a function. One is a linear transformation, and the other one is a pointwise application of a linear function. And in the following, I'm going to talk about convolutional neural nets, who have been all the rage, especially for image recognition, but also as a task, where that linear transformation is a convolution. So this is my simple neuron. So people call that a neuron. You're going to see the biological neuron over there. The point I want to make with this slide is that's where the analogy ends. For me, the neuron here is just that simple thing here that performs a function. What's interesting here, you're going to hear me talking about the weights that define a model, and those are the W's in that function, is how much you weight each input to that function to obtain a result. Just to set up the vocabulary, this is an example of a deep learning approach. I'm going to be training on the top, on the left. So I'm taking a bunch of images that are my training set. I'm going to push them through my DNN, push back, and I'm going to train that network, meaning I'm going to find the W's that do that when I push a dog, then in the later stage of inference, I can infer it's a dog. So the whole training phase is discovering the W's once I set up the architecture of that green network here. Why is it deep? Just because I have a lot of layers here. The difference between machine learning and deep learning is just there's a lot of hidden layers in those neural networks, at least for neural networks. Some more vocabulary. Going from left to right here is going to be what we call the forward propagation. And going from right to left is going to be the backward propagation. You can see the difference between those two stages. Training will have to go in both directions. I forward, and then I wiggle my weights back to set up my model. And I have that iterative process. Inference, it's only forward propagation. And in terms of computing, that's going to be slightly different. Just order of magnitudes. We heard about supercompute. We've been doing machine learning before we had to use big GPUs and everything. What's different with deep neural nets is actually the size of the objects. A network like that is around 1 billion parameters. That means to train those things, you need a lot of data. And when we say a lot, like 100 million images is very common. 1 billion images is common too. In terms of the learning algorithms, we're talking about 30 exaflops in general, and having training time from 1 to 30 GPU days is not uncommon. So if you've been doing molecular dynamics, it's not uncommon to you. But if you've been doing machine learning, that's relatively new. And that's where we go from workloads that were much more, workstation-style workload or small workloads to the real HPC or supercompute world. OK, so what's the challenge? It's already old, it's already almost 2 years old, like 1.5. But what researchers have said is that if you want deep learning research to be better and to be, working well, right now we're still limited by how fast the network can be computed. The second thing is, for the inference, sometimes you're going to hear, oh yeah, GPUs are great for training, but for inference, they're pretty bad. Actually, that's not so clear, and that's not so true. And when you're running inference, the limitation is how fast we can put a set of image into that forward prop thing. And that can be accelerated too, sometime in a different way. OK, why do we care? Because basically all this is very costly. It's costly in power. It's costly in hardware. And if you're in a car, you don't have 500 watts for a GPU. If you're a data center and you have thousands of GPUs, you want to make sure you get the best of it, otherwise it's costing you a lot. This is very much an HPC problem, right? The cost of power in HPC data center has been known for a long, long time. So type of networks for the following. Traditional DNNs are usually fully connected. CNNs have some convolution layer, and RNNs are different. They have some feedback loops. And so I'm just giving that to you here so that you hear sometimes, oh yeah, I can accelerate a CNN, but not an RNN, and so on. It's just for you to have an idea of what the difference is. Okay, so why are GPU good at DNN? This is an example of a fully connected DNN. And what we're doing when we're doing the forward prop, it's basically a big matrix vector. And if you take those matrix vector and you transform that into a convolution, which I'm not going to show, what you have is a matrix-matrix operation. Do you know what people do in LinPack all the time? HPL, a matrix-matrix operation. So basically, we got the same operation you guys have been doing for like a lot of time. Okay, and we can do that matrix-matrix also by something we call batching. So I'm pushing so many images that I'm not going to push them one by one. So batching is just an embarrassingly parallel way of saying, OK, just push like 100 images at a time. And then I automatically have a matrix. And I'm directly in an easy peasy matrix-matrix multiply case scenario. And backpropagation is the same, right? It's basically, and you wiggle your weight, so it's going to be gradient descent on matrices. If you've done molecular dynamics, gradient descent is gradient descent. It's been gradient descent for a while. So those are well known. OK, so the problem is, when you're real time, when you're in a car, it's not necessary that you can do batching, because you might not have to recognize 20 cars in front of you. So basically, what's happening is you have different tricks. You can either reuse the weights, and you can kind of batch all the weights, or you can fuse those things. Also, there's a lot of sparsity in those networks. I have a billion parameter, but sometimes more than 30% are very close to 0. So I can just prune them. I can prune for inference, because it doesn't matter. For training, that's different. So a CNN, so the convolution, so that's an example I've shown yesterday. It's one of the first, most famous deep learning network by Len LeCun. And so basically, this is the pseudo algorithm for this. This is just a big matrix multiply again. And this is 80% of the compute in a classical image recognition workload. So again, no magic here. This has been known for a while, and that's why it can be accelerated pretty well. RNN are slightly more complicated. So basically, this is the structure of an RNN. RNN are mostly used for speech recognitions or things like that when you need to have a memory. And they have a feedback loop. So I'm not going to detail that, but RNNs are not a simple matrix multiply like I've shown you before, but you can always come back to your matrix multiply, even with that feedback loop. Other operations we do, so you're going to hear things like, oh yeah, did you do pooling? Or for those that did the training yesterday, we asked you at some point to add a ReLU. Those operations are not limiting factor. Like, we have a lot of them, but they are so benign compared to the rest of the workload that it doesn't really matter. Deployment on the hardware. So training, we can see, are we going to go to the data center? We're going to come back to that. But for deployment, if you have a car, if you have a drone, or if you have a data center that where you want to process instant images, the problem gets a little bit different. Because the GPU and the DNN might not be the bottleneck. So when you see those big deep learning machines, often people are spending a lot of money on those super fast SSDs and RAID drive. The reason is you have to feed the GPU. You have to get the data on the GPU, and that's where you get a pretty big bottleneck. So first you have to give it on the CPU, and then you have to push it on the GPU. And so when you're going to see a big deep learning machine, you're going to see usually it has a pretty beefy CPU. And the reason is that. The reason is being able to pull the data and being able to pre-process your data before you send it to the GPU. Do you know any HPC workload that is both CPU and GPU bound at the same time? HPL, again. So the problem is exactly the same. The I/O pattern is going to be very, very different than most of the HPC workload. But the overall bottleneck issues are in the same places. OK, parallelization. So it's very funny to present that to an audience like you, because I'm pretty sure you see where I'm coming at right now. I have a lot of inputs. I have a lot of points. I have a lot of filters. I have layers that are dependent. but I don't have any data-dependent operation. So I can statically schedule everything. What I'm going to do first is I'm going to play on my data. So I said that I can batch, or I can put images that are independent of each other. So the first way to do parallelization for a deep learning approach, or for the DNN, is to basically use what we call data parallelism. So I have two machines here, machine 1 and machine 2. So I can just put different sets of images to both machines. It's going to work all fine. They're going to train a different model. I'm going to have to sync at the end. The good thing is, while I'm computing that, I don't have to sync the models. This can only get you so far. Like in HPC, this is called embarrassingly parallel, if I'm not mistaken. So you still need the synchronization at the end, and that's what's costly. The second way of doing parallel is to do model parallelism. So basically, if I have a very big DNN, I can put half of it on each machine, and I can compute like that. It's good because I can have larger models. The trouble is with that, I need very, very efficient communications between my machines, right? It's most commonly used within a node, or it's been, at the beginning, it was used inside a node because that's what we could do well. That is changing very, very fast. Okay, and the last, even more embarrassing parallel section of deep learning is, we're going to see that, but I don't know whether my model is going to be good from the start. Like I have an idea, I set up my model, but that network architecture, I might want to play with it. I might want to play with those parameters. So if I have 3 designs I want to play with, I can just launch those 3 designs at the same time and see which ones is going to get the better result. Okay. GPUs for deep learning, fast and efficient. This is how it scales. So that's a simple example of data parallel. So we can see right away why data parallel is going to scale very well. Model parallel is a whole different beast. And one of the challenges right now is to get there with model parallel too. For RNN, people say GPUs are bad at that. That's an example from Baidu from 1.5 years ago. That's pretty good scaling, I think. So it's feasible. It has like the constraints I've shown before, especially in terms of sync, but that works well. Okay, I want to go fast because I want to take some time at the end to show you something. So sometimes you hear about reduced precision. You've heard about, FP16, int8, and why are we making such a fuss about reduced precision? So not computing, like having a lower precision level allows us to compute with less storage. So you can put a bigger network in your car or anywhere else. It reduces the energy, it improves the performance, and to some point, it doesn't affect the accuracy at all. That's where the big difference with machine learning comes at play. With molecular dynamics comes at play, for example. I mentioned gradient descent, but we never use in deep learning second-order gradient descent, for example. Those are all first order, and we don't need a lot of precision. So just as a reminder to everybody, that's what I call FP32, FP16, int32, int16, int8, with the accuracy, which is here. And so basically, in my workload, I can do the weight updates and the sum as the main operations, and I won't be affected too much for some operation by a loss of precision. And so 16-bit is a good spot because it's a good balance between my prediction accuracy and my energy. It's a good spot for training. It's a good spot for inference. 8-bit precision is also feasible for inference. I'm just going to go fast to that. I invite you to have a look at those papers. So this is training in FP16. So if you're training with reduced precision, you're going to need a bunch of other tricks. And there's one which is called stochastic rounding. And I mean, I'm not going to give more details, but the less precision you're going to have, the more algorithmic tricks you're going to need to use. Okay, in production. That's fine. It's a bunch of academic papers. That's great. But what do we do? In production, that's what the life of a deep learning scientist working for a large company looks like. So I got my workstation. I manage my data. I bring that to my data in my data center. I have a big repository. I have to augment my data, make sure I have enough We discussed that yesterday in the tutorial. That could be simple things, just like flipping your images. Then I'm going to have to test and train, figure out which architecture I want to use for my network, and keep on doing that. And then I'm going to deploy. So training, deploy, inference. So I can deploy on my drone, can deploy in my data center, or I can deploy in my car. And in terms of hardware and software, so in terms of software, that's going to be all the same. But in terms of hardware, that's going to be slightly different. And that's where I got very interested by the panel yesterday, because I have HPC on the left. I have HYPERSCALE data center on the right. For me, I mean, there's something I shouldn't say, but it's almost the same. The difference here is going to be you might not need as many interconnect between the machine, but it depends also, are you batching things? If you have a very large model, you might want to have that too. So, I mean, at this point, what is HPC? What is supercompute? What is HYPERSCALE? I don't really know. OK, training. So I'm sorry I forgot. I changed bag yesterday. I brought a piece of hardware for you to look at. I brought the whole new P100 Tesla GPU. So this year we had a new GPU that looks very different from the previous GPU we had before. It has a new interconnect. It has a new HBM2 stack memory. And also it has like a new way to program memory and to use memory on the GPU. And I'm going to detail that a little bit more. So since I forgot, I have another surprise for you at the end. So it uses a new interconnect. I'm not going to detail. I give a link later on to a nice white paper you can read that has all the detail. I'll be here to answer any question you have. This is the HBM2 stack memory. I see I'm late, and I have 5 minutes left, right? OK. And unified memory is pretty cool. Because basically, you can say, hey, I have 2 GPUs. Each of them has 16 gigs of memory, but I want 32. So I can allocate beyond the GPU memory size, and I can basically tell the GPU, hey, can you give me 32? And the system's going to automatically manage to give you those 32. You don't really care anymore where those are. And if you've been in CUDA classes, like I've been teaching CUDA recently, you just like host to device, device to host, and you explain those events and how to deal with the memory. I hope that in 2 years from now, I won't have to teach that at all anymore, because a lot of people struggle with that. And that's basically what this is. OK. This is the baby. That's where we put those 8 GPUs connected together. This is the DGX one. So that's a server that we designed for deep learning or for AI. It has 170 teraflop performance, half precision performance, and it has 8 of those GPUs that I've shown before. They are connected in a kind of like complex topology, but it's not as complex as we might think. It has 2 CPUs. Each has 2 PCIe switch, 8 GPUs, like the regular 8 GPU server you can see. But those 8 GPUs are also connected through NVLink in an 8-cube mesh. So those violet links here are actually a cube. Interestingly here, you have those 2 things. In the machine learning world, those are not very famous, but in HPC, those are just standard. Those are IB cards. And what I was saying before, that you have to feed the GPU and you have to feed the machine, is done through a super fast interconnect, also between the boxes. OK, so I have a small video. I'm just going to try to make it quick because I like it very much. It shows what there is inside in the box, because the box doesn't fit in my purse, so I can't bring it. So this is the box. As you can guess, it has to be ventilated pretty efficiently. The 8 GPUs are not with the classical PCIe connector. They are flat on the GPU board. Those are the drives. We only use 4 super fast SSD drives in there. The power supply is relatively beefy. You have to power those GPUs. And then there's a lot of attention which is paid to the airflow. And you're going to see in the video, one of the most important points for this is how those things are connected. So this is the NVLink connectors that connect the GPU between each other. And the next step is how do we go out of the box using those IB cards. And those have like 4 InfiniBand EDR boards, plus the networks, the regular networks is separate. And below is the CPU board. As you can see, those are relatively beefy CPU. We basically have to feed those GPUs. Interestingly, yesterday in the panel, people mentioned, okay, it's good to have hardware, but you have to be able to run on that hardware. And that's exactly what we cared about very much. So basically, the box comes with a software stack that is containerized and tuned for the box. So I like very much that people like DK and the Gaikai guys came before me because they got to show the software stack, which I won't have to do. So there's no reason not to put that machine in the top 500. It's very good at metrics, multiply. So we took 124 of those machines, and that makes a cluster, which is 28 at the top 500. But it's also the most energy efficient one, being first at the green 500. OK, so we optimize all the software stack. We tune them. We work with most of the frameworks provider to provide the best performance for the box. And that's an example with CNTK, with one of the fastest deep learning training frameworks right now on GPU, developed by Microsoft. So, and for the DGX, we work with several frameworks providers to provide the whole stack, all containerized. For that, so I'm not going to go on containers. Some people did the job for me, which is very good. So what does it mean? It means that you have an application. You have to pick a framework. And under the scene, we're going to take care of a bunch of things for you. Those are the neural net operations, mostly the convolutions and other stuff. Those are the sparse operations and the algorithm you need to train. And those are the collectives. And underneath the scene, we take care of all of this for you. OK, inference, I'm going to pass very fast. So it's a different problem. We have a different software stack. And we have that software stack to be able to use the same code and the same model that you could be able to train in FP16 or FP32 and then deploy in FP16 or int8. Those belong to different type of hardware that are P40 cards that you might be familiar with, or the smaller new factor P4 so that you can fit in any web server. Those are embedded platform. I don't want to detail that. I know Steve likes demo very much. So I provided you with link to know more about it. And I'd like to do a quick demo, if you don't mind. Do you have 5 minutes for a demo? OK. OK, so I just hope it's not going to crash. So this is a DGX one. I'm not lying. It's a real one. So I'm sorry, some people said, yeah, be careful, terminal. If you're scared by the terminal, that's not a demo for you, but I'm sorry, that's all I have. This is a real DGX one. Indeed, you can see the NVLink connection. That's actually the topology of the machine. And you can also see the InfiniBand cards. OK, so now, my machine is not doing anything. So first, I'm a data center person. What I'm going to do is I'm going to start my monitoring. So I'm going to pull a container. Yeah, I know, in privileged mode, but just because it's easier for a demo. I'm going to pull my container, and I'm going to start my monitoring. While it's starting, so it's still not there yet. Yeah, it's here. So this is the traditional monitoring system you might have in your data center. There's nothing fancy here. I can change the refresh. OK. And I can see, I'm going to be able to see my machine is not doing much. OK, so now I'm going to go to my NVIDIA repository. And I got a container registry where basically for all DGX user, we provide a bunch of tuned containers. And so what I'm going to do, I could do it, I can see the different version of the container, see example, download it. So I'm going to do it directly from the machine. I'm just going to pull a TensorFlow container. I might have this one already. No, I don't. So I'm just pulling my TensorFlow container. Actually, I did the pooling stage separately. I could have run it, and it would have pulled itself. OK. Should I wait? Yeah, OK, I'm going to wait. I can see that my machine is still not doing very much. Anything. OK. And now what I can do is I can run that container. So I'm going to run the exact right version. So basically what I'm going to run here is an 8 GPU training. TensorFlow experiment on ImageNet. So I'm starting TensorFlow. So as you can see, the system is a little bit, it takes some time for it to start. I can see what I'm doing. I'm very well tuned. Like I have 16 gig of memory. I'm using 15 dot a lot. So it's good. And then I can see my GPUs are going to wake up slowly. So what's very costly in a deep learning strategy is to start it, right? The experiment lasts a long, long time, so we start it. I can see that the system has detected my topology here, the local matrix stuff, and it's going to be able to use the NVLink for doing the multi-GPU run. So generating the model, that means it's mostly pulling from the drive, pulling my images, pulling everything. So here, I can see my disk usage is rising, so my data is coming there. And the CPU load has started to get interesting. Initializing. I'm sorry, it's a little bit like watch it pad dry, but when it's going to start, it's going to be more interesting. In the meantime, I can take questions.
For the monitoring, do you use traditional monitoring like a daemon that is running, or do you use the Docker stats that you can gain?
No, for this, so basically for this, we hadn't thought about the monitoring, and Doug sitting here like a few days ago said, hey, yeah, okay, I'm just going to put the traditional Grafana like everybody's used to do. That's why we're running privilege mode. It's just like, it's just a regular Grafana that we pull.
Yeah. And what version of Docker are you running? 1.13?
Yes.
So you can get the Docker statistics out?
I could, yes. I just didn't do it. I could. So it's starting, so I don't have a lot of images per second in the beginning, just because the first run is not a real run, and then my experiment is really starting. And when my experiment is really starting, my GPUs are also really starting. So I can see my training as started for real. And the machine using cache, so I'm only going to see one disk pooling because my dataset fits in a RAID cache, and then it's not going to be read anymore. Okay, yeah. It TensorFlow. I mean, I can show you the ugliness of a Python script, but so yeah, TensorFlow using so it's the basic interface of TensorFlow. It's a Python script. Please say that again.
It's very primitive, the way that the TensorFlow provides you. So I'm wondering how you actually do it. You have to come up with your own.
Oh, you have 8 GPU examples in TensorFlow. They provide some of them. Okay. So the reason why I don't want to show that one, it contains a lot of ugly stuff because you have to process the data. You have to resize it on the fly and so on and so forth. So actually, the training part of the script is that long, like 40 lines. The pre-processing part of the script is 800 lines.
Are you running on one node?
Sorry? Yes, this is only one node. Yeah.
Yeah, very good training, and we have a chance to, experience your product. And my question is, after we finish our 4 lab, and around out of time, can we get the extension, or we can pay to?
Yeah, we can see that offline. Some of them are accessible for free. Yes.
Okay.
Yeah. Yeah. Well, we can take that offline on the tutorial. I see somebody yell at the question. Yeah.
How does when you go back to the running application, how does it know the loss? How does it know the accuracy? It must be not supervised learning.
Oh, yeah. So the way it works, I forgot to say that. So basically, the way it works for deep learning training, you train on the part of the data set, and at every epoch, once you push all the images once, you use a separate part of your data set that you've never seen before, to which you confront your data to. Yes. Oh, yeah. That example, sorry. That example is the basic supervised image classification example. That's basically ImageNet. The funny part of that example, though, is that's an example that 2 years ago took on 4 GPU, it took 1 week, something like that. I'm going to be done in like, what, 10 minutes?
Did you sell it out of your truck? Can we get one?
Sorry?
Do you sell it out of your truck?
We sell some, like we have a website where you have an order button. I'm not a salesperson, so I don't know exactly what the PO looks like. But yes, we have some of them. So this one is one of the very early models. But yeah, a lot of people have some. You're welcome, you know. There's a button on the website. You can just click on buy one.
And what about the jitter? What does that call?
So jitter is, so when we train, as you can see here, among the different, I report the statistics every so and so, and I'm going to have instabilities in the training and so on. So I'm not going to be as fast, especially for backprop. The algorithms sometimes are not exactly the same. So I have some variance in that, and that's what this reflects. Yeah. So basically, it's if you're used to deep learning, if this is 0, 1, you're good to go. Here, you want to make sure that those two numbers are kind of OK, and that's the variance in number of images. I'm doing 763 images per second, plus or minus like 23. I would have a performance problem if that jitter would have been like 200. OK, thank you so much.